getting started, first part we're going to talk about is a little bit about terminology and what some of the terms and some of the words that we use in referring to membrane and membrane systems. So typically when we talk about membrane, we're talking about the very thin layer or sheet, essentially, that rejects or permeates certain molecules depending upon, again, on their pore size. Also sometimes talk about element. What's an element? Essentially the membrane and all its components assembled. Sometimes you hear that term out there. That's what we're talking about. Feed, of course, is the material supplied to the membrane system. Concentrate, sometimes referred to as retentate. Again, that's the stuff that is rejected or retained on the top side of the membrane. The other thing we talk about is permeate. What is permeate? That's the portion of the feed that does pass through the membrane surface. Rejection, we're primarily talking about the ability of the element or membrane to hold back particles. When we talk about clean water flux, what is that? Essentially what we're talking about is at the end of a CIP, we're reviewing the capability of that membrane system to pass water through the system, and then we measure it. Two typical ways of doing that. And the first one is liters per cubic meter. So we're looking at the square meters of the element and its ability to pass liquid per hour, and also gallons per day per square foot is the other one. So liters per square meter per hour or gallons per day per square foot. Primary measurements of permeate flow. So in operating membrane systems, what's really critical and very important to those machines is the quality of the feed and the way that the systems are operated. So to get the best optimal performance out of the system, we're looking to ensure that we have the fines removed. So, knowing we discussed last week of the tight tolerances and the mesh that are inside these elements. So any kind of particles, especially cheese fines, are very difficult to remove out of the system. So having that removed through clarification or fine savers, and having those equipments operate at their peak condition, plus having pre-filters in place in front of the machines will eliminate that problem. Also, fat removal. Most systems are not designed unless they're up front and say like a raw milk UF or a MF system designed to remove fat. If you get higher concentrates of fat in a 35 system, typically at a 0.08, or a WPC system 80 at about a 0.06, or a WPI 90 at a 0.01 fat. We like to stay at that or less than. Pasteurization, again, ensuring the products are pasteurized up front helps knock down or control micro. So ensuring pasteurization, we're talking about 162 degrees for 16 seconds. And operating systems cold is always best, trying to keep them below 70 degrees. Some systems are mandated to operate at that level, and some are not. Process temperatures, processing hot. When we process in that danger zone, that area between 70 or 45 and 135, product can grow exponentially. So ensuring that we're staying either warm or hot or cold to stay out of that danger zone. That 120 degrees, you can see product can go TNTC very, very quickly within an 8 hours of operation. Can also have calcium fouling can occur at those temperatures. You can have also, you can end up with protein gelling if you get a severe pH change. You could also end up with biofouling, that you get this biofilm that starts to grow on the surface, and then that in turn could lead to very difficult to clean systems. And then That in turn leads to utilizing heavy oxidizers, which then can impact the life of the element. Processing cold, you end up with bacteria is virtually inactive. So as you get into those lower temperatures, bacteria doesn't become a big of an issue. It doesn't have that time for it to grow. You get better protein rejection. Calcium phosphate then does not become as prevalent. You don't end up with protein gelling. Since you don't have the microgrowth, it's less susceptible to biofouling, becomes easier to clean, and you end up with longer element life. Now we're going to talk a little bit about the two types of systems that you see out there, mostly the dead end filtration and cross flow. Dead end is essentially the system where, like a filter in your car, right? So dust will accumulate on the surface over time, and the filter ends up plugging, and then you have to take it out, replace it, put in a new filter, and run for a while until that again happens. Or you end up with taking it out, banging it on the ground, what have you. But that's not what you want to do, right? Also, dead end would be like the pre-filters, the sock filters that you have in front of these membrane plants, or sometimes other parts of the facility where you're looking to remove larger particles. Once they get dirty, they're thrown out. So conventional or dead end filtration. Again, dead end filtration is when flow is applied to the surface, and the permeate particles will accumulate will flow through, and the larger particles will accumulate on the surface. Over time, the pores will start to be plugged off by those larger particles that are left on that surface as they build. Flow filtration. So an asymmetric membrane surface. So again, asymmetric, we talked last week, all the pores are not necessarily exactly the same size. Really, on cross flow, we're relying on the ability for product to flow across the surface and the smaller particles to pass through the permeate through. That tangential flow across the top of the element causes that shearing effect that helps minimize the boundary layer of gel and that fouling layer on the bottom of the surface. Also, that higher flow creates that turbulence that we discussed last week. Remember, turbulent flow as it goes across that mesh screen helps to remove that and reduce. It doesn't necessarily all remove, but it minimizes and reduces the level of fouling. So the element will run for extended runs versus very short life from a conventional dead end filtration. If you have a reduction in that cross flow, you can end up with lots of issues. So if the flow rate is reduced or too low, that boundary layer will start to build back up. So you won't have that turbulent flow that you need, and the boundary layer will start to increase. That high velocity turbulent flow keeps it free. Without it, the product run will start to decrease. Cleaning cross flow. So during CIP, during standard cleaning, we'll use to return the system back to its clean water flux rates, right? Get that system back to new. And to do that, it requires the hydraulic action in order to get that high flow to remove the products off the surface. So you can add chemistry. Chemistry helps us to loosen and soften, but you need that turbulent flow, that high cross flow velocity in order to move that soil off the surface. And if you happen to lose that cross flow, then you should needs to be addressed immediately. So that should be one of the areas during your audits that you should be looking for and reviewing.
I am now going to talk a little bit about how we actually get that cross flow. As Carl showed you in the diagrams previously, if we do not have the correct cross flow over the membrane surface, we will see the gel layer, the fouling layer, the boundary layer building up, where we will then see high pressure and low flux rates. So we're impeding the permeate flow through the membrane, and the efficiency of the whole process decreases, and then it's time to shut down and clean the membranes. So most membrane systems run for about a 20-hour run, and then we see them shut down the system and set up for CIP. So that's kind of where we come into it, but not understanding the system hydraulics and performance in production. If we don't understand that, we can't provide a good cleaning CIP recommendations. What you see here is just a very basic diagram of a system flow and basic membrane operation. We have a feed balance tank, and coming off that feed balance tank, we have a feed pump. That feed pump is the driving force or supply to the membranes. So that would typically be set at a set flow rate for our product coming into the membrane systems and the housings. And then the square box in the middle is kind of the membrane loops or stages. On this one, there's 3 of them. And I'm actually just going to kind of bypass that, because most of the section I'm talking about will be talking about what's in that box. But what we have to look at is what goes in is the feed, is the green line. It will either come out as permeate, which is the smaller molecules that will permeate through the membrane, and then the concentrate, which is the molecules that will not pass through the membrane and retain on the top side of the membrane and build solids as we go through the system. Depending on your desired product, your permeate may be your finished product, particularly when we look at polishers. The finished product is the permeate, the purified water that's gone through. But we also look at a microfiltration system that's defatting whey protein concentrates. The finished product for that microfiltration system would be the permeate. So the fat molecules would be retained, the valuable protein molecules would pass through, and the permeate would be the finished product. But the majority of the systems that we do work with, whey protein concentrates, whey milk protein concentrates, etc., the finished product is that concentrate, that retained product line. So depending on your process will depend whether the permeate's the finished product or the concentrate is the finished product. So I'm just going to go through a very basic example. This is an example here. We're talking about reverse osmosis, and it's a very simple concentration factor, because pretty much everything that's permeates through the membrane is water. Now, if you're looking at a UF, an MF, or a nanofiltration, you have to have a calculation, a mass balance calculation. Typically, your customer will have that, or the OEM will have that, or the membrane manufacturer will have the mass balance for that system. Because you have to, what goes in, the solids going in, they will be divided into the permeate and the concentrate. So you have to be able to do that mass balance. But for this example, it's very simple, because the permeate is just water. There should be no solids in there. Everything else is captured in the retentate concentrate. So I have a product stream that is at 5% solids. My goal is to get to 15% solids. Now, that may be that I can further process it at 15% solids. It may be that I'm going to truck it out somewhere to a different location, and removing the water will save me on reduction in transportation costs, etc. So my goal here is to get from 5% solids to 15% solids. So I have to figure out my concentration factor, and it's really easy for an RO system. It's 15 divided by 5. That gives me a 3x, or 3x concentration. So what I do, and I need that number, it's a very valuable number, I need that number to then calculate how I would design the membrane system. So my feed supply is coming to the membrane system at 150 gallons a minute. So out of that 150 gallons a minute, I need to determine how much has to be concentrate and how much of it has to be permeate for me to achieve that number, that 15% solids. So basically what I do is I take the 150 gallons a minute, divide it by 3, which is my concentration factor, which gives me 50, which means I've got to have 50 gallons a minute of concentrate. So remember the first diagram, what goes into a membrane system has to come out. So the remainder has to be 100 gallons a minute permeate. So an OEM equipment, original equipment manufacturer such as Tetra Pak, such as Gia, CFR, MSS, Colaris, the people we work with, MP&C, they would take that 100 gallons per minute permeate. They would know the temperature that we're running at, etc. And they would figure out how much membrane area it would take to create 100 gallons a minute of permeate. Once they have that number, then what they do is they have to calculate how many stages or loops to get the system to work efficiently. So from this, you can see that the design was it's going to take 3 loops with 3 8-inch vessels, or whatever size they are, to create the correct mass balance and design for the system to work. So our feed going in is at 150, our permeate coming out is 100 gallons a minute, and our concentrate is at 50 gallons a minute. So that 50 gallons a minute of concentrate coming out will be at 15% total solids. Okay, so we're going to follow the flow. What and where is the baseline? So the baseline is the pressure that's that driving force to force the molecules through the membrane. If you can remember from last week, we had a little kind of science lesson there talking about osmosis and reverse osmosis. So what we're doing is reverse osmosis. We're forcing those smaller molecules through the membrane. If we don't have that driving force, those molecules will not pass through the membrane. It takes energy to go through that membrane. So they're going to go on the path of least resistance, which is across the surface of the membrane. So we would have no separation take place. There'd be no permeation. So the driving force is that baseline pressure. And the baseline is that yellow line that runs along the bottom there. So we have our feed tank, and we have our feed pump, and we have a flow meter. That's where we set our 150 gallons per minute. Now we have the 3 loops, and I will talk about the flow on that in a minute. But then you can see on the back end, which is the right-hand side of the diagram, we have the yellow line that runs all the way along. That is our baseline. That is the driving force that's going to provide the separation on loop 1, 2, and 3. It's the same driving force. And you can see then there's a valve, the little green valve, and then another magnetic flow meter. So that magnetic flow meter is measuring the flow rate. Now, if the flow rate is not at 60, if it's lower or higher, it will send a signal to that ratio control valve, and it will tell it to open up or close down so it can hit the 50 gallons a minute. And that's the same with the feed pump. It has a flow meter, and if that pump is running too fast or too slow, it can send a signal to control that pump to the set point of 150 gallons a minute. Our baseline is really important. It's the driving force through the membrane, and we have to remember that terminology, baseline pressure. The other thing that you'll see is that green line, which is our permeate. You can see that 100 gallons a minute coming out of there. I'm just going to talk a little bit about kind of the flow or the basic membrane operation here. What we've done is kind of done a snapshot of the loop number 1. We're going to talk a little bit about that cross flow. Carl mentioned how important it is to have the right cross flow, the turbulent flow. It's the scrubbing action across the surface of the membrane surface to stop the molecules building up on the surface with the boundary layer, the fouling layer, and to keep that surface swept clean so we can continuously allow the permeate to come through the membrane. by example, you can see on loop 1 that there are 3 vessels or housings. With membranes, there's a lot of terminology that's interchangeable. So you can see that there's 3 of them there. Each of these housings or vessels need a certain flow rate depending on the diameter of them. Many years ago, we would have 3.8 or 3.8 inch elements. We would just typically call them 4-inch. But we see nowadays most membrane systems are either 6-inch or 8-inch. Just means that they're getting bigger footprint, etc. So as the diameter of that vessel increases, so is the need for the flow that goes through it. It's like cleaning of any pipe. The bigger the diameter, the higher the flow to get the velocity that you need to clean it. Okay, so for my example here, I have 3 8-inch housings. Each one of those housings needs, say, a minimum of 100 gallons per minute flowing in. Now, in each of those housings, there probably is 3, 4, or 5 membranes sitting in there, all of them which will need flow across them. Okay, so this is where we come into looking at our pressure differentials and those flows. Okay, so from my feed pump, it's supplying me with 150 gallons per minute. It is going to feed into loop 1. Now, if I did not have that recirculation pump, which is the pump feeding into the house, if we could just ignore that for a minute, if that pump wasn't there and I fed into my housings at 150 gallons a minute, I would only have 50 gallons a minute going through the 3 vessels. That 50 gallons a minute, if you remember, I said I need a minimum of 100 gallons a minute per vessel, that would provide me with very low flow across the surface of the membrane. And I always kind of describe it as kind of going down the lazy river, kind of bumping off things, and you're in a tube and you're not really pushing anything along. So what we do need is we need to boost that flow of the feed to get us the correct flow rate. So what we put in is a recirculation pump to increase that flow rate into those housings. So I'll have 133 gallons a minute because that pump provides me with 400 gallons a minute. That provides that scrubbing action cross flow over the membrane surface. And I kind of say that's a little bit like a whitewater rapids. It's kind of got that scrubbing action. It's going to move those soil across the surface of the membrane. Every membrane system will always have stages or loops. And for this example, it's called loop because we got these images have been provided by Tetra Pak. So we're very grateful for letting us use them. What we can see is each loop has its own pump. That pump is providing that cross flow over the surface of the membrane. Okay, so from here, we can just look at the numbers. We've got 150 gallons going in. The pump needs 400 gallons a minute. So if we just go up to the pump, we've got our 400 gallons a minute. We come through the membranes and we've permeated 50 gallons a minute. What goes in has to come out, and we've got 350 coming down to our baseline. Now, whenever we start up a membrane system, it's always flooded with water because everybody says, how does it catch up? Where does it get, where does it get that 400 gallons a minute? Well, that liquid was already in there. So when that pump starts up, it's not starting dry. There's water in there, and it will just start to kind of recirculate that water, and then the feed solids will be introduced. It just takes a while for the water to permeate out, and we start to build solids. So whenever you start up a membrane system, you'll always start up with a building up solid step before you go forward, just so you can hit the right solids that go to the silo. What we've got now is we've got the 350 coming down to the baseline. The pump needs 400. So coming down to the baseline, the flow will split. 250 will come and join the 150 to make my total of 400 coming out of that recirculation pump. We will be then left with 100 gallons a minute. That will feed our second loop. At that point, at that intersection of where the 350 comes down and joins that baseline, There's no orifice plates, there's no splitting valves or anything like that. It's just the equipment manufacturers design the pipes and the pumps, balance it really well to create that recirculation to give us that cross flow over the membrane surface. So at this point, our solids now feeding into loop 2 is about 7.5% solids. So we're not where we need to be, but we're about halfway. Well, we are halfway because we're trying to get to 15. So that first loop's done quite a bit of work, removing a lot of the water here. So I'm going to go on to the next slide and now show you the whole system. So what we're seeing now is kind of the same diagram, but we've included the extra loops. We're just going to talk a little bit about the pressures and what those pressures mean, because we don't have a magnetic flow meter coming off each of those recirculation pumps. If it's so critical to have that cross flow over the membrane surface, how do we know what those pumps are giving us? How do we know that we've got the right flow rate into each vessel? Because there's no flow meter. We use the pressure gauges. So every pump, recirculation pump, will have a pressure transmitter or a pressure gauge on the outlet of the pump. So basically what's going into the membranes or the vessels, there will be a pressure transmitter. And then what we could do is we could take the, we take the baseline pressure. If you follow the baseline all the way towards the concentrate valve, you will see a pressure transmitter and it will show your baseline pressure. For this example, it says 15 psi. Now, if I was to put a pressure transmitter on the outlet of the vessel coming down to the baseline on each of these loops, you will see that that number will still be 15. So it's the number going in and the number coming out. We see a pressure drop. And we want to see a pressure drop. A pressure drop is an indication of flow. And I always do an example of you put your thumb on the end of a garden hose, and if you had a little pressure gauge there, you would see pressure build up because you're restricting flow. Now, what happens when you release your thumb off the end of the garden hose, the pressure will drop to show there's an indication of flow. So that's what we're looking for. We want to see a pressure differential, but we want to see that pressure differential at the correct number for the membrane type that's in there. Now, the different spacer sizes are on the feed mesh, and as we become more viscous, the solids increase. We need to increase our spacer size through the membrane system. And that changes a little bit of the dynamics here in our pressure differentials. So on a 31 mil, the loop 1, we'll do a quick calculation to determine what that pressure differential is. We typically want to look around 10 to 15 psi pressure differential on the 31 mil. So I'm going to take my 63 is my inlet pressure. I am then going to subtract my baseline pressure. That gives me 48 psi difference. I'm then going to divide it by the number of membranes that are loaded into that housing. So this example, there's 4. So I'm going to take the 48, which was the differential, and I'm going to divide that by 4, and gives me 12 psi. It's in that range of 10 to 15. So we know that the cross flow in that loop is correct. It's giving me turbulent flow. I'm going to have good scrubbing action, and I'm not going to have any concerns with the hydraulics on that loop. Loop 2, the one in the middle, we've increased the mill spacer size because it may be getting more viscous. And you can see now that the inlet pressure is 75 psi. Baseline is still the same, 15. So 75 minus 15 gives me 60 psi. And I divide that by 4, gives me 15 psi pressure differential. It's a little bit higher, but my mill spacer is higher. So therefore, I need more flow through there because the gap is bigger. I need more volume through there to provide that cross flow. And then the last one is 65 mil spacer. And my differential, I've already calculated for that. It's going to be about 18 psi, which is about where we want to be. It's really important to understand and know what the mill spaces are in every stage or loop of the membrane system that you work with. So if you can remember back to those that did the membrane challenge last year, that was one of the questions we asked, what is the mill spacer? And then you did your calculations. And from there, we can determine whether it's in range or out of range. If it's below the range that we recommend, then we would get that lazy river flow. We would probably see premature fouling in production. And then also we would probably have some issues with CIP because we wouldn't have that scrubbing action. If the pressure differential is out of range or too high, we can have some compaction and crushing issues on the membrane itself. And you can see the feed spacer material. We call that vector migration. You will see that migration through, and you could see a crushing, kind of almost like taking a soda can and crushing it with your foot. It kind of wrinkles, and that can have an impact on membrane life just because you're creating some stress on the membrane. So it's always important to know what those pressure differentials are. And we always refer back to the membrane manufacturer's guidelines. We typically follow Koch membranes, K-O-C-H. They do a really good job on specifying spacer size and element pressure differential, whereas some of the other membrane spec sheets just kind of give you a general guideline and don't give you an individual membrane number. So if you need any of that information, it is written in here, but if you want specifics, contact us or go visit the Koch website with your membrane information and you can look that up. Here's what we're looking at now is kind of all the numbers put together, the pressures and the flows, and we kind of can see how everything balances out. With this picture, you can see kind of some of the bells and whistles that they have on a membrane system, because membrane system is basically kind of a bunch of stainless steel pipes, valves, pumps, and balance tanks. And it's kind of hard to see what's going on because you don't actually see that separation take place. So this is really kind of what you would see. The balance tanks will have a temperature transmitter, level transmitter. It's very important that we know what those levels are for CIP so we can determine hold-up volumes. There are pressure transmitters on each stage, or pressure gauges, which is valuable for us to determine that cross flow. And typically then the pumps will also have an output percentage. So we can actually see what's going on with the pumps, whether they're running at the right percentage or output. But what you can see here now is kind of how you go from loop 1, which is we looked at already, 150 gallons per minute of feed, joining the recirculated 250 gallons a minute to make our 400 gallons a minute. And you can see that there's 50 gallons a minute of permeate coming through. At that point, we've got the 7.5% solids and 100 gallons feeding the loop 2. So loop 2 is now seeing 7.5% solids, and we've got 100 gallons a minute there feeding it. We have the same number of housings, so each of those housings needs a minimum of 100 gallons a minute feeding it to give us our turbulent flow. But we do have the larger mill spacers in there, so our pressure going in is a little bit higher to give us the correct cross flow. So we're feeding in now at our 400 gallons a minute. We've got our correct pressure, we've got our correct turbulent flow, and we've got 35 gallons a minute of permeation rate. Do we think that that loop 2 is not working as well as loop 1 because our permeation rate is lower? No, it's working fine. And you will see a drop in permeation rate on the second stage because our solids going in is higher, 7.5% versus 5% going into the first one. And if you remember, we talked about osmotic pressure, which is that driving force to push the molecules through. We talked about if we were on a cruise and we had an RO system, a reverse osmosis system, taking in the seawater, turning it into drinking water and water for showers. And I think we said that they were for Carl's cocktail as well. He wants some ice there in his margarita. if we went to the Dead Sea, our osmotic pressure would be higher and we'd need a different pumping system to create that fresh water. Because the Dead Sea has higher salt content, it has a higher osmotic pressure. So basically what's happened is we have a higher osmotic pressure on loop 2, but we still have the same driving force, which is our baseline pressure is still 15. So if we wanted loop 2 to perform in the same amount of permeate, coming off it at 50 gallons a minute, the same as loop 1, we would have to install another pump to get that baseline pressure higher to force those molecules through. Now, remember, they don't do that. The OEMs don't do that. It's another pump, more expensive energy. So they just design it that they would just see a little bit less efficiency on that one loop. So as you can see, we're going in at 400 gallons per minute. But as we've only permeated 35, our numbers look a little bit different coming out. We've got another 15 gallons coming down, so that's 365 joining our baseline. So we had 100 feeding into loop 2, and then we'll take 300 of that 365, feeding it into that recirculation pump to give us 400 gallons a minute. Now we're feeding loop 3, 65 gallons a minute. That's the remainder. And at this point, we now have increased our solids even more. At this point, we're probably about 11.5% solids feeding into loop 3. And again, we need the 400 gallons a minute flow because we've got the 3 vessels that need at least 100 gallons a minute. And then you can notice that our pressure is higher because at that point now we've got the larger spacers. So we needed that extra flow going through there, or we needed that higher pressure to force that through to give us our 18 psi differential. And then you can see we only permeated 15 gallons a minute. And that again is because our solids going in is 11% solids, higher osmotic pressure, same baseline of 15. So our driving force is the same. So it's harder for those molecules to those water molecules to pass through because we didn't increase the pressure to push more through. But you can see the composite total of the 3 loops is 100 gallons per minute. And then from there, you can see the 50 gallons per minute coming out as our concentrate, which is exactly what we saw on our first slide. So that's our balance there. As I mentioned, our membrane systems are made up of a lot of valves, stainless steel, piping, lots of pumps, etc. What this example shows is an example of a UF system, a microfiltration system that has stage or loop isolation valves. There's those little red valves or whatever kind of triangles that you can see. And basically what you can see here is that we can close those valves and isolate a loop or bypass a loop. And then also what you can see is loop 1 got split into section A and section B. And the reason for that is with the systems that have the larger pore structure, the microfiltrations and the ultrafiltration systems, is that we need to control or limit the total amount of surface area being turned on during startup. So during startup, we need to, limit the amount of membrane area on there. If we didn't limit the amount of membrane area on there, the membrane surface would get completely fouled or blinded by overpermeation, and we might even see a negative baseline situation. So kind of to describe that is, it's kind of hard to describe. I always kind of say it's like you're at a concert venue and there's lots of, hundreds of people in one area, and you're asked to exit through one small door. And what you do is everybody heads towards that one door, and it can only allow one person out at a time. So you get this kind of backlog of people waiting to get through, and you have to wait to get through, and people start pushing and shoving, and it kind of gets a bit nasty, and then there's maybe a blockage, etc. So what we do is we kind of limit that we limit the amount of people going to that door and be a little bit more orderly. So what we do is we would start with bringing on loop 3. We would start backwards, bringing on loop 3. And the reason for that is our membrane system, when it's shut down after CIP, is sitting in water. If we were to start at the front end to the back end, and as we brought on all those other loops, we would be diluting that concentrated 15% because we would be introducing water as we go through. So if we can go backwards, we can kind of get all that permeate out, water out as permeate, so it doesn't create too much of a drop in your finished product. So that's the reason of going backwards. So with this, what would happen is we would open up loop 3, start with loop 3, and once we've hit our set point of our baseline pressure, we would then bring on loop 2, and then you would see a drop in baseline pressure. We could run for a couple of hours or however long, and then we would maybe bring on loop A or B. Baseline pressure would drop. And if you have an account that has a really good trending, you can actually go and see on the trending when these loops come in, because you follow the baseline trend. You can see when it drops, that's when a loop got turned on. So you can determine how long those loops have been running for. Then the other final loop would come on, or A or B, and the system would probably run then for many hours after that, because it didn't over-concentrate, it didn't hit that negative baseline pressure. Knowing when the loops turn on and at what the interval or the time interval between each loop being turned on is a really good indication on how that membrane system's performing. You can ask an operator, he typically knows that loop 2 might get turned on at 1 or 2 hours after production started. And then maybe loop A or B might come on another 2 hours after that. And then loop B comes on 2 hours after that. Now, if all your loops are coming on in between 10 minutes or 15 minutes from the other one loop turning on, there's a problem. It may be that membranes didn't get cleaned properly the night before, or maybe there's something in that feed stream that's causing those membranes to foul. There's something that's not typical, and those operators know. They know how that profile typically looks on turning those loops on. So it's always great to talk to those operators. They know how those systems should run. So that's just a little explanation. If you have a UF or an MF system, go look at those trend lines. You'll see them drop and rise up, and that's where those stages are coming on. Okay, so now we're going to talk a little bit about diafiltration. Diafiltration is adding water to the concentrate section or the baseline. What this does, we typically see this in whey protein concentrates. Anything over and above 70% or higher in protein will require diafiltration. It kind of seems weird that we're adding water back to us to remove the water. Well, basically what it does is help remove the lactose. Lactose is a sugar. It's going to dissolve readily in water. And then if it's dissolved readily in water, it will pass more rapidly or readily through the membrane itself. So we add this diafiltration to wash out the water, wash out the lactose to achieve a higher protein level. So on this diagram, again, courtesy of Tetra Pak, and we thank them, we have an additional tank here, which has got the diafiltration water in it. From here, you can see how they determine where they're going to put that number or that flow. So there'd be a flow meter, and there'll be a valve that controls the flow, and it hits into the baseline, and you can see it's right there by the pump. So it's going to just kind of follow in, get sucked into the pump. So now it's kind of got an additional flow, and you can see how that now kind of changes the numbers a little bit with regards to the permeation rate, because now we've got more water through there. So our osmotic pressure dropped a little bit, so allows a bit more flow. And it just changes a little bit on the dynamics of the recirculation coming back through. Take a look and see if your systems have diafiltration. Like I say, if you're 70% WPC or higher, there'll be diafiltration. These diafiltration lines or sections need to be part of the cleaning, so make sure that's included in the cleaning. Just going to talk a little bit here about how to control your membrane system. So if I needed higher solids, we can look here about total solids, which is really kind of what's coming out of the RO system or nanofiltration. But with these protein systems, we look at protein on a dry basis. So really kind of if we want to increase our protein, if the protein was too high, how can we change that? And we can do it in a couple of ways by increasing or decreasing the concentration factor, which is that ratio control valve, or increasing or decreasing our feed flow rate. So manipulating the front end or the back end, you can change the dynamics of the system. And then also as well, if you want to increase or decrease the total solids by using diafiltration, you can increase or decrease, and you can kind of see the results from that. Again, increase in concentration factor and diafiltration. What does that do to the total solids? Kind of an unknown. We don't want to over concentrate. It will increase the protein by dry basis. We have seen some accounts that have over concentrated and plugged their membranes up with protein, and we do have a special recovery wash for that, which will get discussed next week in the cleaning section. And so there's a lot of ways of manipulating the membrane systems to achieve the solids and the protein levels that you're looking for. Again, this is kind of more of a controls, equipment, customer setup, but it's always interesting to know how the membranes actually are controlled. The final discussion here is really determining the cross flows and the hydraulics, really understanding the knowing what that feed spacer is, knowing what the membrane size is, knowing the number of membranes per vessel, and the number of vessels per stage. So we need to know those, and that's again a Tetra Pak design. This will give you an idea of what those numbers should look like. And we had our 31 mil spacer, we had the 47 mil spacer. I think on our diagram it was 65, but there also is an 80 mil spacer. It was very wide spacer. And obviously as those spacers increase, the cross flow has to increase to give us a turbulent flow. And we determine that by pressure differential per element.